Assalamualaikum warahmatullahi wabarakatuh. A very good day. Okay, now for part number 5, we will discuss about the reheat ranking cycle. So the reheat ranking cycle actually one of the specific method to increase the ranking cycle efficiency. So previously we already learned about the general methods that can be used to increase the ranking cycle efficiency in part number 4. So now we will use what I call few of the method in order to develop specific method for the ranking cycle in order to increase its efficiency. So one of the method, the specific method that can be used is we call the reheat ranking cycle. Okay, the ideal reheat ranking cycle. So in order to increase the efficiency, we have learned that there are three general methods on how to increase the ranking cycle efficiency. Okay, one of them is by superheating the steam at the boiler, where we increase the temperature of the steam so that the temperature of the steam at the inlet of the turbine will be higher, as shown in the TS diagram, from T3 to T3 prime. However, by using this method, we have some disadvantages, where we will have metallurgical unsafe level, where due to the very high temperature at the inlet of the turbine, this will cause the change of the material structure of the turbine blade, and this condition will cause the damage of the turbine blade and will reduce the performance of the turbine. So the second method that can be used to increase efficiency is due to the metallurgical unsafe level, when we increase the temperature of T3 at the inlet of the turbine. So now, in order to solve the problem, we just fix the temperature of T3, okay, and then we increase the pressure at the boiler. Okay. However, by using this method, the quality of the steam during the expansion process will reduce, and this condition will cause the increase of moisture content during the expansion process in the turbine. So this also will cause the damage of the turbine blade, when the moisture content in terms of water droplet will impinge on the blade surface and will damage the turbine blade. Okay, so now if we combine both methods, first superheating the steam method and also the increase of the boiler pressure, so the combination of this method we call the reheat ranking cycle. So now we will discuss about the ideal reheat ranking cycle, where we need to expand the steam during the expansion process, where at least we need to use 2 stages turbine, and in between we need to have a reheating process. For the schematic diagram for the reheat ranking cycle, so the schematic diagram will consist of one pump, one boiler. We will have 2 stages of turbine that consists of high pressure turbine, also low pressure turbine, and also we will have one condenser. Okay, so the water from the pump will enter the boiler, and the boiler will increase the pressure and also the temperature of the water and produce superheated steam, and the superheated steam will enter the high pressure turbine. After the expansion process in the first stage of the turbine, the steam will again enter the boiler for reheating process, where for the ideal case the pressure during the reheating process will be constant. After the temperature increase after the reheating process, the steam or the superheated vapor from the boiler will enter the low pressure turbine for the further expansion process. Okay, so this is the basic schematic diagram for the reheat ranking cycle with 2 stages turbine, and in between we will have reheating process. So in terms of reheat stages, if the number of reheating stages increase, the process will be close to isothermal process, as shown in the TS diagram, and this condition will limit the what I call the potential of what I call of the reheat rankine cycle in order to have the highest value of thermal efficiency. Okay, so now the maximum number of stages in terms of reheating process, we only can have 2 reheat stages, which means we will have 3 stages of turbine, and in between we need to have 2 reheating process. So if you draw TS diagram, so this is the TS diagram for the ideal reheat rankine cycle. So we have isentropic compression from state number 1 to state number 2, constant pressure heat addition process from state number 2 to state number 3, and then because we have 2 turbines, so we have the isentropic expansion process in the first turbine, which is referred to the isentropic expansion process in high pressure turbine from state number 3 to state number 4. And then due to the reheating process, the temperature increase, and the process of reheating is at constant pressure, where P5 equal to P4, and then the steam will enter the second turbine, which is referred to the low pressure turbine. The steam will experience the second expansion process, where the process is isentropic, where S5 equal to S6, and then the steam will enter the condenser for the condensing process. Okay, so the cycle will continue. Okay, so in terms of amount of energy, so we need to supply W into the pump. So we have W in at the pump. Q in, we have 2 Q in. First Q in we refer as Q in primary, Q in 1 in the boiler. So we have high pressure turbine, low pressure turbine, and also reheating process. We have second Q in during a reheating process. So we have Q in 1 and also Q in 2. So in terms of W out, because we have 2 turbines, so we will have 2 W out. W out 1 for high pressure turbine, and also W out 2 for low pressure turbine. And at the condenser we will have Q out. So for the ideal reheat rankine cycle, in terms of phase, state number 1 will be saturated liquid, state number 2 compressed liquid, state number 3 superheated, and at least in saturated vapor. Okay, state number 4, the phase may be superheated or maybe saturated mixture. So we need to check for state number 4. State number 5, normally after reheating process, the phase will be superheated vapor. And then state number 6, we need to check the phase. So the phase may be in superheated or maybe in saturated mixture. Okay, so that's the condition, or in terms of TS diagram for the ideal reheat rankine cycle. So in terms of formula, in order to determine the value of Q in, W out, and so Q out, we need to refer both TS diagram and also the schematic diagram. Okay, in terms of analysis, so for the total Q in value, the total Q in value equal to Q primary. Q primary refer to the amount of Q in that we need to supply to the boiler, plus Q reheat, amount of Q in due to the reheating process, which is also equal to Q in 1 plus Q in 2. So if you refer to the TS diagram, the total value of Q in will be equal to H3 minus H2 plus H5 minus H4. Okay, for W out at the turbine, so we have 2 turbines, so now the total W turbine out equal to W turbine 1 for the high pressure turbine plus W turbine 2 for the low pressure turbine, which is also equal to H3 minus H4 plus H5 minus H6. For Q out, so we only have 1 Q out equal to H6 minus H1, the energy during heat rejection process in the condenser. And W in, because we only have 1 pump, the formula for W in equal to H2 minus H1. So these are the formula that can be used later on to determine the thermal efficiency of the ideal reheat rankine cycle. Okay, now let me look the difference between the ideal reheat rankine cycle and also the actual reheat rankine cycle. So now for the actual reheat ranking cycle, let us consider the reheat ranking cycle with 3 turbines plus 2 reheating process, as shown in the schematic diagram. So in this diagram, we have 1 pump, 1 boiler. So we have 3 stages of turbine. So we have high pressure turbine, medium pressure turbine, and also low pressure turbine. So in between those turbines, we will have 2 reheating process. So we have reheater number 1. So the piping line will re-enter the boiler, and then we also will have the second reheater, reheater number 2, to conduct the reheating process, where the piping line from the medium pressure turbine will re-enter the boiler for reheating process number 2. Okay, so in terms of state, so we'll have at least 8 states will involve. Okay, so we have 1 condenser and also 1 pump. Okay, let's say we consider first we consider the ideal reheat ranking cycle in order to make comparison with the actual reheat ranking cycle. So if we draw the TS diagram, so we will have this kind of TS diagram from state number 1 to state number 8. Okay, so here we can see that we will have 1, 2, 3, 4 constant pressure line will involve, where in terms of process, so we will have 1 isentropic compression at the pump. So we will have what we call 3 isentropic expansion in the turbine, as shown in the TS diagram. So in terms of phase, state number 1 will be saturated liquid, state number 2 compressed liquid, state number 3 after the heat addition process, the water will be in superheated vapor region. After expansion process, the condition for state number 4 may be saturated mixture, may be superheated. And then we have reheating process from state number 4 to state number 5. So the phase will be in superheated vapor, and the steam will enter the medium pressure turbine for the expansion process, isentropic expansion process, and then come out from the turbine for the second reheating process in the boiler, and the temperature will increase again at state number 7, and then the steam will enter the low pressure turbine and come out from the turbine at state number 8. So state number 7 will be superheated, state number 6 may be superheated, maybe saturated mixture, similarly with state number 8. Okay, so we need to check the state number 4, number 6 and number 8, whether the state or the phase is within saturated mixture or superheated vapor region. And in terms of energy, so we need to supply W in at the pump. So we will have Q in number 1 at the boiler, Q in number 2 during reheating process number 1, Q in number 3 during reheating process number 2. Because we have 3 stages of turbine, so we have 3 W out. W out number 1 at the high pressure turbine, W out number 2 at medium pressure turbine, and W out number 3 at low pressure turbine. And we have 1 Q out at the condenser. So in terms of characteristics, in terms of properties for the ideal reheat ranking cycle, so we will have entropy value S2 equal to S1, S3 equal to S4, S5 equal to S6, and S7 equal to S8 due to the isentropic process in the pump and also in the turbines. And in terms of during reheating process, P4 will be equal to P5 equal to P reheat number 1, and P6 equal to P7 equal to P reheat number 2. And during the heat addition process and also heat rejection process, so P3 equal to P2 because we have constant pressure heat addition process for the ideal Rankine cycle. P8 equal to P1 due to what we call constant pressure heat rejection process in the condenser. And normally in terms of temperature after the reheating process, the temperature normally will be restore same as the temperature at the inlet of the first turbine. So now we have, for the ideal reheat ranking cycle, T3 will be equal to T5 equal to T7. So in terms of formula W in, W out, Q in, Q out, so W in will be H2 minus H1, Q in, total Q in will be Q in 1 plus Q in 2 plus Q in 3, which is equal to H3 minus H2 plus H5 minus H4 plus H7 minus H6. For W out, we have 3 turbines, so we need to combine W out number 1, W out number 2, and also W out number 3, which is total W out equal to H3 minus H4 plus H5 minus H6 plus H7 minus H8. And we have 1 Q out at the condenser. The value of Q out equal to H8 minus H1. For the actual reheat ranking cycle, so if we draw the TS diagram, so the process will involve pressure drop, temperature drop, and also the isentropic efficiency at the pump and also at the turbine. So now we need to involve the point S and also point A. S stands for isentropic state, A stands for the actual state. Okay, for example, at the compression process, so now we need to consider 2S for the isentropic process and state 2A for the actual compression process in the pump. Similarly, in the turbine, for example, for turbine number 1 for high pressure turbine, so we need to consider state 4S for the isentropic expansion process and also state 4A for the actual expansion process in the turbine for the high pressure turbine. Okay, so now we need to consider state 2A, 4A, 6A, and also 8A as shown in the TS diagram. So we'll have W in actual, Q in 1 actual, Q in 2 actual, Q in 3 actual. So in the turbine, we will have W out 1 actual, W out 2 actual, and also W out 3 actual. So in the condenser also we need to consider the actual state. So where we have Q out actual in the condenser. So in terms of state or phase for each state, so normally state number 1 can be saturated liquid, and normally for the actual one will be in compressed liquid. For state 2A, for sure the state will be in compressed liquid. So the rest explanation in terms of phase similar like for the TS diagram for the ideal reheat ranking cycle. Okay, so we need to check the phase for each state in the actual reheat ranking cycle. So in terms of properties, thermodynamic properties, so S2A will not equal to S1, S3 is not equal to S4A, S5 is not equal to S6A, S7 is not equal to S8A because the process is not isentropic. And P4 might be not equal to P5, P6 also normally not equal to P7 during the reheating process. And during heat addition process, normally we will have pressure drop, so P3 is not equal to P2. Similarly with the heat rejection process, the pressure will be not constant, so P8 is not equal to P1. And the condition after the reheating process is not constant, it's not equal. So T3 is not equal to T5, not equal to T7, okay, due to the heat losses and so on. Okay, in terms of formula, so W in equal to H2A minus H1. So all the formula involved with the actual heat ranking cycle, we need to consider the actual enthalpy value for the actual state. So for W in, the formula will be H2A minus H1. For Q in, total Q in for the actual process equal to H3 minus H2A plus H5 minus H4A plus H7 minus H6A. W out, total W out for 3 turbines will be equal to H3 minus H4A plus H5 minus H6A plus H7 minus H8A. And the last one, the formula for Q out will be H8A minus H1. Example 4.4. Consider a steam reheat Rankine cycle. Steam entered the high pressure turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at the pressure of 10 kilopascal. If the moisture content of the steam at the exit of the low pressure turbine is not exceed 10.4%, determine A. the pressure at which the steam should be reheated, and B. the thermal efficiency of the cycle. Assume the steam is reheated to the inlet temperature of the high pressure turbine. Okay, so these are the information that given in the question, where we have 15 megapascal and also 600 degrees Celsius, the condition at the inlet of the high pressure turbine, which is referred to the first turbine. And then the pressure at the condenser is 10 kilopascal, and the question gives you the value of moisture content 10.4%. So from the value you can determine the quality of the steam. And the question asks you to determine the pressure during reheating process. For question A and question B, you need to determine the thermal efficiency, where you need to assume that the steam is reheated to the inlet temperature of the high pressure turbine, which means after the reheating process, the temperature at the inlet of the low pressure turbine will be same as the temperature at the inlet of the high pressure turbine. Okay, so T inlet for high pressure turbine will be equal T inlet at the low pressure turbine due to the reheating process. Okay, now from the question, draw the schematic diagram in order to see the clear pictures of the process for the reheat Rankine cycle. So for this case, we assume that the reheat Rankine cycle is ideal, is an ideal cycle, where we have a boiler, a pump, a condenser, and also we have two turbine, high pressure turbine and also low pressure turbine. So in between the two turbine, we will have a reheating process in the boiler. Okay, according to the data given in the question, so we have because we consider the ideal reheat Rankine cycle, we will have constant heat rejection process at the condenser. So P1 will be equal to 10 kilopascal and P6 also equal to 10 kilopascal, and we have 15 megapascal for P2 during heat addition process, because during heat addition process for the ideal reheat Rankine cycle, the pressure is constant. So P3 also will be equal to 15 megapascal. So the value of P2 we obtain because the question already give you the value of the inlet of the high pressure turbine in terms of pressure and also temperature, where the question give you the value of pressure and temperature, where which is equal to 50 megapascal and also 600 degrees Celsius. So automatically, what I call for the ideal case, P2 also will be equal to 15 megapascal. For the reheater, for ideal reheating process, P4 will be equal to P5 equal to P reheat, the pressure during the reheating process. And as mentioned in the question, after reheating process, the temperature at the inlet of the low pressure turbine must be equal to the temperature at the inlet of the high pressure turbine, so that from this statement, T5 will be equal to T3, which is equal to 600 degrees Celsius. So these are the information that we can obtain from the questions given. And then draw the TS diagram. So this is the TS diagram for the question. So we have isentropic compression in the pump. So compression start from state number 1 to state number 2. Heat addition process in the boiler at 50 megapascal. Inlet temperature for the first turbine, for the high pressure turbine, at 600 degrees Celsius, where T3 will be equal to T5, 600 degrees Celsius. And we have isentropic expansion process in the turbine, in the both turbine, for the high pressure turbine, so low pressure turbine. And the last information that we have we have the value of moisture content equal to 10.4%. So from this value we can determine the value of quality of the steam for state number 6, where X equal to 100 minus 10.4, so we'll obtain the quality of steam will be 89.6% or 0.896% as shown in the TS diagram. So from the data we can use to determine the enthalpy value for each state, and also we can determine the pressure during the reheating process. And all this value we can use to determine the thermal efficiency as requested by the question. So now you need to determine the value of P4, which is equal to P5 equal to P reheat. And then for question B, you need to determine the thermal efficiency of the ideal reheat Rankine cycle. Okay, solution for example 4.4. So question A, the question asks you to determine the pressure at which the steam should be reheat, which means you need to determine the pressure of P4 or P5, which is also equal to P reheat. Okay, so the figure show the TS diagram and also the schematic diagram, where we need to refer to this diagram in order to understand how to determine the specific value for each state. Okay, so now what you have to do, it is better to determine the important parameters such as entropy and also enthalpy value for each state from state number 1 to state number 6, where we need to make sure that at least we need to have for each state we need to have 2 data. Okay, so before we answer the question, we need to determine the enthalpy value for all the states involved. Okay, in terms of data given, so P2 equal to P3 equal to 15 megapascal, T3 equal to T5 equal to 600 degrees Celsius, P4 equal to P5 equal to P reheat, where we need to determine P1 equal to P6 equal to 10 kilopascal during heat rejection process. Moisture content given at the outlet of the low pressure turbine, which is referred to state number 6, equal to 10.4%. So from this value we can determine the value of X at state number 6, which is 1 minus 0.104 equal to 8 equal to 0.896. So from this value for sure we know that for state number 6 the phase will be in saturated mixture, because we have the value of quality at state number 6. And in order to determine thermal efficiency, we can use this general thermal efficiency equation, where we know that if we look at the TS diagram and also the schematic diagram, the value of the formula for Q in will be H3 minus H2 plus H5 minus H4, and Q out will be H6 minus H1. So that's why we need to determine the value of enthalpy for each state involved. Okay, for state number 1, so because the cycle is ideal, so we know that the phase for the state number 1 is saturated liquid, and we have the pressure for P1 equal to 10 kilopascal. So we already have 2 data or 2 information. So from these 2 information we can determine the important value for state number 1, especially the value of enthalpy. Okay, so by referring to the saturated water pressure table, so at 10 kilopascal we can determine the value of H1, where H1 equal to HF at 10 kilopascal. So H1 equal to HF at 10 kilopascal equal to 191.83 kilojoule per kg. And from the table also we can determine the value of V1, where V1 equal to Vf at 10 kilopascal equal to 0.001010 meter cubic per kg. And also maybe we need to manipulate the value of entropy later on, so we can determine the value of entropy for state number 1, where S1 equal to SF at 10 kilopascal equal to 0.6493 kilojoule kilogram Kelvin. Okay, done state number 1. State number 2, the state will involve process from state number 1 to state number 2, where the process involves the isentropic process. And we know that after the compression process, the state will be in compressed liquid. And if you look at the pressure value for P2, the value is 15 megapascal, where the pressure is greater than 5 megapascal. So the data for the state number 2 is available in the compressed liquid table. So we can refer to the compressed liquid table to determine the value of H2. So now we need to have two information. To use the table, we need to have at least two information. So now we have pressure P2 equal to 15 megapascal. They are already given in the question. The other data is the value of entropy, where we can manipulate the isentropic process, where S2 equal to S1 equal to 0.6493 kilojoule kilogram Kelvin, where the value we already obtained from state number 1. Okay, from this data and the phase compressed liquid, use the compressed liquid table at 15 megapascal. So you need to find where is the location of the value for S2, and then the value will be in between 0.5666 and also 0.8234. So you need to make interpolation between the value of entropy and also the value of enthalpy. Then from the interpolation you will obtain the value of H2 equal to 207.5 kilojoule per kg. Okay, so you have an alternative in order to determine the H2 if you don't want to use the what I call the compressed liquid table. However, this method you will have I call few percent of error, but the value, if you look from the calculation, the value is still acceptable. Okay, so you can use the formula involved with W in, where W in we know that equal to V1 multiplied by P2 minus P1 equal to H2 minus H1. So V1 we already obtained in step number 1, P2, P1 we already, the question already given in terms of value, and the value of H1 also we already determined in step number 1. So rearrange the equation, we can obtain the value of H2. Okay, where H2 equal to 0.001010 multiplied by 15,000 minus 10 plus 191.83, so the value will be 206.7 kilojoule per kg. So if you look, if you compare between the value of H2 they obtained from the second approach and also the value of H2 from the compressed liquid table, the difference is not much. So our priority, because the pressure is 15 megapascal, it is better to use the compressed liquid table for the accurate value of H2. However, still you can use the second approach by using the formula for W in equal to V1 multiplied by P2 minus P1 equal to H2 minus H1, because the value is still acceptable. Okay, next, state number 3. So the pressure given P3 equal to 50 megapascal and T3 equal to 600 degrees Celsius. So we already have two data. Let's say you're not sure the phase for state number 3, so you can check the phase by using saturated water pressure table. So at 50 megapascal, you just determine the saturated temperature, where the saturated temperature is equal to 342.24, and compare the saturated temperature obtained for 50 megapascal with the temperature of T3 equal to 600 degrees Celsius. So T3 greater than this T saturated temperature, so confirm the phase is superheated vapor. So now we need to refer to superheated water table at 15 megapascal and also 600 degrees Celsius. So from the table you can determine the value of H3, where H3 equal to 3582.3 kilojoule per kg. And also you can determine S3, maybe later on you can use this value to manipulate the asymptotic process to determine the other value for the other value at different states. So now we have S3 equal to 6.6776 kilojoule kg per S3 equal to 6.6776 kilojoule per kg Kelvin. Okay, so done state number 3. State number 4. State number 4 will involve the asymptotic process for the first turbine, high pressure turbine. So we know that because process asymptotic, S4 equal to S3 equal to 6.6776 kilojoule per kg Kelvin. We don't have any information about P4. So for state number 4, at this moment we only have one data, so we cannot use the table to determine the enthalpy value for H4. Okay, because at least to use the table for the water table, thermodynamic water table, so at least you need to have two information. But for state number 4, at this moment we don't have enough information, so we cannot determine the phase, and also we cannot determine the value of H4. So we will find the state 4 value later on. So now we proceed to the other state that have enough information. So if you look, the state that have at least 2 data is state number 6. State number 5 also, we don't have enough data to determine the value of enthalpy and so on. So now we determine the information for state number 6 first, where we know that P6 equal to 10 kilopascal, and we have the second information or second data where X6 equal to 0.896. So we already have 2 data, so we can determine the value of enthalpy, entropy and so on for state number 6. Okay, so because the value of X6 already given, automatically we know that the phase for state number 6 is in saturated mixture, because we have the value of X. Okay, so now in order to determine the enthalpy value and also the entropy value for state number 6, we cannot get the value directly from the table, but we need to use the specific formula for enthalpy and also for the entropy for the saturated mixture region, where for the entropy, S6 equal to SF at 10 kilopascal plus X6 multiplied by SFG at 10 kilopascal. So the value of SFG at 10 kilopascal we can determine from the saturated water table at 10 kilopascal. X6 already given, so from the equation we can determine the value of S6. So from table at 10 kilopascal we can determine SF value 0.6493 and also SFG value, which is equal to 7.5009. So substitute into the equation, so you'll get S6 equal to 7.3701 kilojoule per kg Kelvin. Okay, similarly to the enthalpy for state number 6, we need to use the equation H6 equal to HF at 10 kilopascal plus X6 multiplied by HFG at 10 kilopascal. The value of HF and also HFG at 10 kilopascal we can determine from the saturated water table. So at 10 kilopascal, HF equal to 191.83 kilojoule per kg and HFG equal to 2392.9 kilojoule per kg. Substitute this value into the equation of H6, so we can determine the value of H6. H6 equal to 2335.87 kilojoule per kg. Okay, so that's the value for state number 6. Okay, after we already determined state number 6, now we need to determine state number 5. Okay, still we cannot determine the state number 4 because state number 4 we don't have enough information. But for state number 5, we can manipulate the data that we obtain for state number 6 in order to obtain the important parameter for state number 5. So from this state number 5, in terms of if we can determine the pressure for state number 5, we already answered the question for the question A, where the question A asks you to determine the pressure at which the steam should be reheated, where the pressure actually is referred to the value of P5. Okay, for state number 5, the process involved with isentropic process at the low pressure turbine, process 5 to process 6, and the temperature given is T5 equal to 600 degrees Celsius. So we only have, at this moment, we only have one data for state number 5. However, because we already calculate the important parameter for state number 6, and the process for state number 5 involves the isentropic process, so now S5 also equal to S6, where the value of S6 we already obtained from state number 6 previously. So SF equal to S6 equal to 7.3701 kilojoule per kg Kelvin. So now for state number 5 we already have two data, temperature data and also entropy data. So enough information to obtain the enthalpy value and also the pressure value. Okay, so if you look after the heating process, normally the state will be superheated. So state number 5 is in superheated vapor region. However, if you want to check whether the phase is correct or not, so you need to use the same procedure where you need to refer to the saturated water table. Okay, saturated water table, and determine the value of SF and SD, and compare the value of SF with SF and SD from the table, and then you can determine the phase. Okay, so confirm after you compare by using the table, also you will obtain that the phase for state number 5 will be at superheated vapor region. Okay, now in order to determine the pressure, so you need to manipulate the information that you obtain from superheated water table. So you need to extract the data in terms of enthalpy and also the pressure value for constant temperature at 600 degrees Celsius as shown in the table. So for example, in the table we have the table for pressure at 2.5 megapascal at 600, and then you extract the value of S. And then for the next table at 3 megapascal at 600, you need to extract the value of S. And you need to create your own table in terms of pressure value and also entropy value at constant temperature of 600 degrees Celsius as shown in the table. So the table shows, the second table shows the column for the pressure and also the column for the entropy. Okay, so now from the table, for the second table, you need to find the location for the value of SF in the table. So the value of the value of S5 in the table. So you need to find the location of the value for S5, which is equal to 7.3701 kilojoule per kg Kelvin in the table. So the value will be in between 7.4339 and also 7.3688 in terms of entropy value. And the pressure value will be in between 3.5 and also 4 megapascal. Okay, so from the table you need to make interpolation. So from the interpolation, the value that you obtain for the pressure of P5 will be equal to 3.99 megapascal, more or less equal to 4 megapascal. And this value also equal to P4 and also equal to P reheat. So from the value we already answered the question for question A, the pressure at which the steam should be reheated, the pressure during reheating process. Okay, so now we already know the pressure, so use the pressure that we already obtained, where P5 is to 4 megapascal. Okay, by referring to the superheated water table, the pressure of 4 megapascal at 600 degrees Celsius. From the table, you can determine the value of H, where H5 equal to 3674.4 kilojoule per kg. So you can obtain directly from the table. Okay, now we can determine the important parameter for state number 4, because we already determined the value, the important value for state number 5. Okay, for state number 4, because the process also isentropic from state number 3 to state number 4, and we know that P4 equal to P5 equal to P reheat. So P4, now we need to use P4 equal to 4 megapascal. And we know that S4 equal to S3 equal to 6.6776 kilojoule per kg Kelvin. So we already have two information, so enough data in order to use the specific table. So because we still not sure the phase for state number 4, so we can use this saturated water table based on pressure to determine to check the phase for state number 4. So at 4 megapascal, determine the value of SF, because we have the information in terms of S4 value. So we need to find the value of SF and also SG. SF equal to 2.7964, SG equal to 6.0701. So make comparison in terms of SF and SG value with S4 value. So S4 is greater than SG. So the phase for state number 4 will be at superheated vapor region. Okay, now you need to refer to superheated vapor table at 4 megapascal, and you need to find the location of S4 value in the table. S4 equal to 6.6776 kilojoule per kg Kelvin, and value will be in between 6.5821 and so 6.7690. So you need to make interpolation between entropy value and also enthalpy value. So from the table you can determine the value of H4. H4 equal to 3154.38. Okay, so we already have all the information in terms of enthalpy for state number 1 until state number 6. Okay, so we already determined all important parameter or important value in terms of enthalpy for all states from state number 1 to state number 6. So now we can determine, or we can answer the question B, where we need to determine the thermal efficiency of the cycle. Okay, so the calculated enthalpy data that we obtained previously. So H1 equal to 191.83 kJ per kg, H2 207.5 kJ per kg, H3 equal to 3582.3 kJ per kg, H4 equal to 3154.38 kJ per kg, H5 equal to 3674.4 kJ per kg, and the last one H6 equal to 2335.87 kJ per kg. So we know that the equation for thermal efficiency equal to W net divided by Q in equal to 1 minus Q out divided by Q in. And if we use the second equation for the thermal efficiency, 1 minus thermal efficiency equal to 1 minus Q out divided by Q in, so we need to determine the value of Q out and also Q in. So Q in, if we base on the TS diagram, so Q in will be equal to H3 minus H2 plus H5 minus H4. So substitute all the enthalpy value into the equation. So Q in will be equal to 3894.82 kJ per kg. And the formula for Q out will be equal to H6 minus H1. Substitute the value. So Q out will be equal to 2144.04 kJ per kg. Substitute the value of Q in also Q out into the thermal efficiency equation. The thermal efficiency equation for this question for the ideal reheat Rankine cycle will be equal to 0.449 or 44.9%. That's how we settle or we answer the question involved with ideal reheat Rankine cycle.